So with that, I think we can start the second session of today. Thank you for the previous one, and I think we had a lot of great discussions around human intelligence, artificial intelligence, what it actually was, and what is limiting computers to be able to think, make decisions, do predictions, etc. Now, for the second part, I want to show you some application areas of this technology. Because when we look at the trajectory of progress for artificial intelligence, only in 10 years, we have made remarkable progress. And in order to illustrate this progress with use cases, we're going to look at 4 different application areas. So we're going to look at computer vision. That is the ability for a computer to be able to analyze visual content, basically to be able to see, both in images and in videos. We're going to look at natural language processing. So this is the ability for a computer to be able to communicate with us humans, understand written language and text. Then we have deep reinforcement learning. We talked about that a little bit in the previous session, but from a theoretical standpoint, where you had an agent in an environment that can be in different states, and in those states, it took actions. So in simulations, we can actually have these agents so that they can train themselves, for example, to be really good robots in manufacturing, collecting stuff on production pipelines, or to train AI algorithms to be able to play computer games, for example, or board games. Last but not least, we're going to talk about generative models. So generative models are a way for computers to actually be creative, imaginary, to have a fantasy, and come up with things we humans have never seen or done before. But let's start with computer vision, because that is the first field that was revolutionized by this deep learning revolution. So I said that we are in the Renaissance period of artificial intelligence as a technology. And computer vision was the technology to get disrupted first by neural networks and AI. Only 8 years back, to solve this very simple problem that I talked about before. So the problem we're trying to solve is to be able to predict if an image that we show to our AI algorithm either contains a cat or a dog. This is called a binary classification problem. It's binary because we only have 2 outcomes. It can either be a cat or a dog. Traditionally, what researchers did before they used machine learning and deep learning to solve this was that they hand constructed so-called feature maps. So the best computer vision researchers in the world, only 10 years back, they would tell the computer how to make decisions on a task like this. So what they would do is that they would design these so-called feature maps and tell them, look for the color orange. Look for whiskers, there are these patterns. Look for eyes, there are squinting. Look for specific edges, that could be ears. And then they would say some patterns relate to cats and some patterns relate to dogs. As you can imagine, that took a lot of time. That could take years and years. So my alma mater, where I started my university degrees, was in southern Sweden. It's called Lund University. They had one of the best computer vision labs in the world before the deep learning revolution. It was one of the crown jewels in academia of Sweden. They published a lot of great research, and they could produce an accuracy on a task like this that was up to 85, maybe 87%. That means that 30% of the images that you've shown to these models were actually wrong in their predictions. Today, we're instead using neural networks. So on this slide here, you can see a schematic representation of a neural network. First, you have the input data, that would be the image. You feed that into the first hidden layer. So these are the parameters, the weights, the neurons of the neural network in the first hidden layer. You can think about them as the rules. So according to the patterns of the input data, some of these neurons will spark and transfer information forward in the network. So whatever information we have in the input image, that will give a specific output here down the network in the different hidden layers we have. And then at the very end, we will have a prediction. That's a probability of what class we're looking at. And here, we're making the correct prediction. It's saying that the probability is higher that this is a cat than a dog. So we're predicting cat. Nowadays, so I said the best computer vision labs in the world, 87% accuracy. In my courses at UC Berkeley, this is the first example we give for constructing a neural network. And it's very easy to, even with my computer here in only 5 minutes, get an accuracy that is over 98%. And the best models in the world would be up to 99.5%. And then you would have some dogs and cats that were very similar to either like dog or cat. It's almost impossible to make the correct prediction. So we've gotten really far, but we can also concentrate on much more difficult problems. So that was a binary classification task, only 2 different output, cats or dog, kind of simple. There is one very, very famous computer vision challenge, and it's called ImageNet. So it's coming out of Stanford University in California, the main rival of UC Berkeley, but still great research. Now, ImageNet is a data set and a competition. So just to explain the data set, a research group at Stanford compiled almost 1.5 million images. And as I said, we did supervised machine learning. Then we know that we have the correct labels for all of the data that we're looking at. So every image in this data set is associated with 1 out of 1,000 unique object categories. These categories can either be a ping pong ball, it can be a tennis ball, it can be the planet Mars, it can be, I think, 17 different breeds of dogs, 14 different breeds of cats, it can be cars, tractors, etc., etc. So this competition has been running since 2010. And as you can see, this graph here only stretches to 2017. It's not that I have been lazy and not updated this, but they stopped running the competition in 2017 because of how powerful AI algorithms got in solving this. So all of the best computer vision practitioners in the world, both from industry and academia, would compete in this competition. They would take this data set, train their models, and then the Stanford research group that ran the competition, they would have some data on the side with like 20,000 images that they hadn't trained on, that they would benchmark the solutions on. So people would submit their models, and then they would get a score on how good the models were. So what you can see here is the error rate for these models. And it's actually the top 5 error rates. So what this indicates is that how many times are you making an error on the images that you see, so that the correct category is not in the top 5 that you're predicting that it is. And the best models in the world in 2010 and 2011, before they used neural networks, so these are called shallow models, was 28 and 26%. That means that more than every 4th image that were being shown to the best models in the world were wrong in their predictions. That's kind of crazy. It's not good at all, to be honest. Then something remarkable happened, because from one year to another, the error rate actually dropped by 10 percentage points. People couldn't believe that this was true. And that was the first year that a neural network was used in order to win this competition. I mean, that's a remarkable drop. If you think about from 2010 to 2011, it was only 2 percentage points. Ever since then, so there was a neural network with 8 layers. We saw the layers in this image. This has 4 layers. This one had 8, and then they become deeper. It's 8 again, 19, 22, 152, and then it can be several hundreds of layers deep now. But as you can see, it goes from 16 all the way down to 2.25, and then we start overfitting to this data set. I mentioned that in the previous session. That's when you train and pick up patterns on the training data that is not supposed to generalize with the models. One thing, so we talked about human intelligence in contrast to artificial intelligence. It was not even possible for computers to basically analyze the visual world before the deep learning revolution. But now they have become very sophisticated in a short amount of time. If I were to give you this task, So I said, okay, you need to study these 1,000 categories. You need to know them by heart. The 17 different breeds of dogs, 14 different breeds of cats, planet Mars, ping pong ball, etc., everything that I said. You can study that for, let's even give you 2 months. And you study really hard so you know them by heart. Then I give you 20,000 images to actually categorize or predict, classify over 2 days. What do you think that your accuracy would be approximately? How well would you do on this task? Or let's not do you yourself, don't benchmark yourself, but a person, an individual. Yes, but let's take a standard human being or a very smart human being. Not even 30%? No, you get 3 months to practice. Yeah, hopefully more than 30%. 98%. So we make errors 2% of the time.
Yeah, I don't know how much.
No, but let's say that it's 1,000 or 2,000, but we need to make it statistically significant. No, but 2% is a good guess. Yeah. Anyone else want to challenge that? Could you be better or would it be worse? For all of those that think that you could do better than 2%, raise your hand. For all that think that you would get a worse error rate, raise your hand. Okay, so everyone thinks that they will get 2% exactly. Then we have the guests from the room. Thank you for participating. So we actually have a human benchmark, and it comes from probably a very smart individual. So the AI director at Tesla, his name is Andrej Caparti. He was a PhD student in computer vision at Stanford at the time when this competition was at its peak. That's around 2013, 2014, 2015. He was obsessed by computer vision and pushing that field forward. But he was constantly nagged by the thought that how well will we humans perform? How close are we to a human benchmark? So what he did was actually that he paused his PhD studies. So one of the most prominent PhDs at Stanford at the time said, I'm not going to study anymore. I'm not going to do research. I'm not going to teach. I'm actually going to study this data set and only look at these images, get to know the categories. So he did that for a couple of months. And then he put himself to the test. And bear in mind now, he's the AI director of Tesla, probably fairly smart. His error rate was 5%. So as you can see already in 2015, we exceeded human capabilities on this task. And if we go forward to the capabilities today, then you can see how it's gone up. And this is the top 1 accuracy. That is at over 87% now. That means that we're choosing the correct image. And some of them are very similar to one another. It's almost impossible to distinguish, for example, an orange ping pong ball against a black surface and the planet Mars. I've looked at both of them, and I would say that either both are ping pong balls or the planet Mars, because they're kind of pixelated, not high resolution. So a lot of progress in this field, but we can do more with computer vision than only classifying images. So one thing would be, okay, which one out of these 1,000 categories do we have an object around? We can also do classification combined with localization. So then we would say, okay, we have a cat in this image, and the cat is within this red bounding box that is also being drawn by the AI algorithm. You can see that up here. We can do object detection. Then we're detecting several objects in one image. So we can detect a cat, a dog, a duck, etc. And then maybe even more sophisticated, we can do instance segmentation. So we can tell whatever pixel areas in an image actually relate to what object. This can also be translated to video. So in real time, we can do object detection right now on any type of video. Here you can see a live stream from Times Square in New York. And we have an AI object detection algorithm that is able to say where we have people, where we have traffic lights, where there are cars, trucks. I even think it recognizes handbags. Whatever objects we train these algorithms to detect, they are very capable of doing so today. And only 10 years back, it was science fiction that computers would be able to do any type of real-time video object detection. It only took a couple of hours when the pandemic became a problem for researchers to actually apply this to application areas that helped us combat the pandemic. So here you can see object detection algorithms. They are even recognizing people. So here we don't print out the identities, but it will say who these people are. And that's according to the looks of the people, but also their gait, like how they're walking, etc. Then whenever you get into proximity of a person so that you're actually in risk of transmitting the disease, this was early on in the pandemic, the bounding box around the person will turn red. Then they will have identified, okay, you have been socializing, you haven't kept your distance. And if one of these people then gets affected by COVID, it will alert the other people. It was very easy to take what we have done in object detection and transfer that to that domain. We can do other things as well. I know that the monitor and the screen isn't that big, so you might not be able to see here in the top right corner. But basically, we have image captioning here. So we can show neural networks and AI models an image and ask it, what is happening in this image? And then the AI algorithms will produce a caption and explain what happens in the image. So here the output is man in black shirt playing guitar. We have construction worker in orange safety vest working on road. It's very, very accurate. And you can even do that with YouTube videos today to get a summary of what is happening in the clip, whatever is happening in the transitions between different scenes. So you don't need a human to create the type of metadata to actually like use the keyboard and put in what is happening in all of the clips and watch the clips. But AI can do that for us. Computer vision is also enabling a lot of new application areas in robotics. So here you can see a simple robotic arm. And what that has been trained to do is to use computer vision in order to detect a shoe. And not only this shoe, but also the tongue of the shoe. Then whenever it sees that, has identified that, it will use kind of like its limbs, etc., move down and grab it by the tongue. And that also requires the perfect pressure, the perfect angle to actually pick up the shoe and then grab it and leave it in the box. This was very, very hard to do only 5 years back. And now AI has enabled us to do that automatically. In manufacturing, we can also use computer vision in order to track when we, for example, assemble products. That the person that is doing that, whenever they are through this process, they are actually carrying out all of the different steps in the right order. And whenever they look at the end result of the product, it can say if it looks good or if it has some defects. So we don't need human intelligence to monitor this or do quality assurance. And from the human movement and assembly of products, we can even create robotic arms that does it for us when they have watched humans for a while. That is all about creating data that we talked about in the previous session. Computer vision is also what is leading the advancements in autonomous vehicles and self-driving cars. So what you can see here in the top right of the slide is a video of a Tesla. It is driving out from a residential area, up on a freeway, and then onto a highway. It's doing that without the driver actually touching the steering wheel. Again, something that would have been science fiction 10 years back. Does anyone know what a Tesla is using in order to make decisions? What did you say? GPS? That's part of it. But do you think a GPS is enough? That will only tell you the location, but not what you have around you, right? Yes. And what type of sensors? Because sensors is right. What? So they are equipped with some ultrasonic sensors, and ultrasound can measure the distance to objects. So that is 100% true. But they are using that for 0.2% of the use cases when they make decisions. We are talking about computer vision. What do you think that they have as sensors? Yeah, in the dark, it's a little bit of thermal imaging. Yes, thank you. Bingo. The answer was maybe more simple than what you thought, but it's cameras. So Elon Musk, when he decided to make the self-driving car, there are two different routes that car companies are taking. Some of them are using LiDAR and cameras. So LiDAR is basically a laser sensor. It's mapping up the environment, looking at distances to objects with a laser. And that laser is scattering laser beams all over the place, 360 around the car. Elon Musk said, because we humans only use our vision to be able to determine the proximity of objects, what we have around us, what is happening, mainly, maybe a little bit of sound with our ears, but mostly vision, a car should be able to function with vision as well. So a Tesla is equipped with 8 cameras around it that creates a 360 view around the car. And that is the main input of data that they're using in order to make decisions. So here at the bottom, you can actually see a little bit of, they're doing instance segmentation that we talked about before. It's actually mapping out, okay, here we have the road, here we have some buildings that they are red. We have some sky that is gray. We have some trees, they are yellowish. So they're mapping out the complete environment at all times with computer vision. Right now, the computer vision algorithms and the self-driving cars, they are at level 3 autonomy. I'm going to take a quick pause here. Welcome. So people in the car industry, they have defined different levels of autonomy for the car. And the self-driving cars we have on the roads today, they are at level 3. So what it says here is that the driver doesn't have to keep their eyes on the road in certain situations. A Tesla today is really good at driving itself in common situations. So what you have here, actually leaving a residential area, driving up on a freeway and then onto a highway during the day, very common situation. When you have the Teslas driving around in San Francisco, in Berkeley, they can mainly drive themselves. However, if you get to a situation where you're driving in the northern parts of Sweden that I visited this summer, then it can be very foggy, it can be rainy, it can be dark. Then these self-driving systems don't work really well. Now, Elon Musk is very much of an optimist. So he has said that to have a steering wheel in a car 5 years from now is going to feel very anachronistic or obsolete. He has said that will almost be like today riding down the highway on a horse. I think that he's way too optimistic. In 5 years, we will still have steering wheels in the cars, and humans will need to take over in certain situations. However, it's amazing what has happened in only a couple of years. The reason why I think that Elon Musk is optimistic is that these systems are not safe and robust against certain attacks. One type of attack is an adversarial attack. That means that you try to trick the computer vision system into making the wrong predictions and decisions. 2 research projects at UC Berkeley that I was involved in. One was looking at the object detection algorithms that were in Teslas. And bear in mind, they can detect many different objects. So one example is if you have 3 dogs here on a bed, then if you don't do anything with the image, it's very easy for the object detection algorithm to actually classify where the dogs are, create these bounding boxes, and do the object detection. However, if you add some noise to the image, and these are pixelated noise, so this image down here has been manipulated. It's not possible for the human eye to recognize that we have done anything with that image. However, we are throwing off the computer vision algorithm. So here it detects that the pink box is a train. The green box here is a cow. And then down here in the blue box, we have a person. So it completely misclassifies what's in the image. So if someone could get a hold of the global fleet of Teslas, inject some noise into the camera feed, all of a sudden it would throw off the self-driving system completely. Another adversarial attack that we also showed at UC Berkeley is that you can only with physical duct tape on, for example, a stop sign. So if you have white and black tape like this, in that exact pattern on a stop sign, then the object detection algorithms won't recognize a stop sign, but it will say that it's a speed limit sign and you should go for 45 kilometers per hour. So this is something that you could do yourself, that you can go up to a stop sign, and if you get that pattern correct, all of a sudden, all the cars that are in autopilot will speed through that. And that can be lethal. So they are not really robust and safe. Other risks with these systems are that they cannot handle outliers. So whenever they are presented with situations that they haven't been trained to handle before, they can actually get into accidents. So here to the left, you can see a Tesla in autopilot. All of a sudden, we have a yellow barrier appearing to the left. The Tesla hasn't been trained to handle that type of barrier. This was a couple of years back when the systems weren't as robust. Whenever an accident like that happens, it won't happen again. Important to know. But you can see it crashing. And here we have a video stream from Taiwan. So on the highway, we have a truck that is flipped. The Tesla thinks that that's a continuation of the road or the sky or whatever. It doesn't recognize the truck. And here you can see when it starts braking, just after passing the person who is trying to have it to stop, it's way too late. Then it's the ultrasonic, proximity sensors that starts to catch, or why we have a huge object in front of us. So whenever you have events that they haven't been trained on, that they haven't seen before, all of a sudden you can get into accidents. My main takeaway from this that I would like to pass to you is that whenever you're training systems like this, so many people are using also computer vision, not only for self-driving cars, but you might have AI doctors that, for example, can look at pictures of your skin to detect if you are in the risk of developing skin cancer. They can look at X-rays of your lungs in order to detect tumors. And all of a sudden, you don't need to rely on a doctor. This could be very valuable, especially for developing countries where it might be hard to train physicians, etc. But many of these algorithms work really well in lab settings. So when they are developed by research teams, they will be in special circumstances and environments where everything is fixed and rigged. And the data they are collecting and making analysis on is perfect. Whenever you deploy that in the real world, so Google had a really cool research project where they tried to detect diseases in the eye. That worked really well in the lab, but then they deployed that to hospitals in Thailand. And all of a sudden, the performance of the AI algorithms were much worse than the doctors they had in Thailand. And in the lab, the AI algorithms kept on beating the doctors all the time. But in the real world, the lighting conditions were different. Here we have lighting conditions so that I can be seen on the camera. They had that in the lab as well, so that it was perfect for the retina scans of the eye. But then in the real world, completely different, and people couldn't handle the systems. You also need to collect a lot of data from different circumstances. So as I said, in order for a self-driving car to be able to drive during the night, you need to collect a lot of data from night driving. You cannot only collect data during the day. And I think that for a long time, we will need hybrid systems. They are not going to be completely autonomous. We will need humans in the loop. We will need a steering wheel. If we humans want to take control of these systems, we should be able to. However, I also don't think that we should only look at the headlines. Every time a Tesla crashes, then you will always see that in a newspaper. They will write about it and how horrible it is. People also get into accidents. What is good about the AI systems is that they don't get tired. They won't get drunk and drive. They won't make stupid mistakes because they haven't taught themselves to handle specific situations if they have been trained on it. So these systems are only going to become smarter and smarter over time. And that's on a global level, because every Tesla that is collecting data, that data will feed into the cloud with the Tesla intelligence, and then all the cars will be updated with that intelligence. So if self-driving cars are more safe in general than human-driven cars, I would say that we should make a bet on rolling out this technology for the safety of everyone on the road. But in order to do so, we also need to make sure that the cybersecurity systems in these vehicles are perfect. We don't want someone to hack into the global fleet of Teslas. Only imagine there are hundreds of thousands of Teslas out right now driving. And if we made all of them instantaneously turn left, many of them would get into lethal accidents. So they should be unhackable, these systems, so that we can trust them. That was computer vision. Kind of fascinating. Did you know that we were this far with these like image detection? Because they are better than humans right now at detecting things in video streams from cameras. Now I'm going to talk about generative models. So in the previous session, we said that AI was not able to be creative, that it couldn't dream or fantasize or have an imagination. Now I might prove that statement wrong. So generative models started in 2015, so 6 years back now. Then what Google did was that they looked at all of the computer vision algorithms they had trained on YouTube videos in order to classify things in those videos and write that metadata on what's happening. They did that automatically. Then they took those networks that made the predictions on what was happening in the videos, and they actually reversed the prediction. So they fed in noise into the output and then asked the algorithm instead to generate an image. So it's almost like the algorithm is dreaming. What you can see here is some output from that. So if you distort an image like this one of manta rays or manates, then all of a sudden you will see that it turns like into this psychedelic picture. This is the same thing. That is a pear that has been like fed into one of these networks in reverse, and all of a sudden it will look like some weird creature. And that is a field of grass. So in some ways, we can almost see these algorithms as they are capable of dreaming as well, because they are making up stuff that maybe we humans couldn't have made up. And that's from their understanding of the world. What's possible to do with generative models as well, almost in the same way that we saw before, like generating things from these networks, is that we can transfer one image to be in the style of another image. So here we can see the painting Starry Night by Van Gogh. Let's say that we had a picture that we really liked and we wanted that to look like it had been painted by Van Gogh. Now with generative models, we're able to transfer the style of Van Gogh onto that image. We can also take the style of, like, if we have a video of Fox jumping on a bed and we wanted that in a pixelated style for an animation video, we can transfer that style automatically. We don't need to do any adjustment as like humans. And here we have the artist, I think that's Kandinsky, and we have the Mona Lisa. And let's say that we wanted to have a version of Mona Lisa like it was painted by Kandinsky. Then we can do that as well. And that is called neural style transfer. This has all been enabled by a type of neural network that is called generative adversarial networks. Now, the way that they work is that you have a generator that will produce almost like fake outputs. So this is generated output from an AI, and you want that to be as genuine as possible. So this example here that I show you is handwritten digits. So let's say that we have a data set of 100,000 handwritten digits, very easy to collect. You can get that online. But then we wanted to train an AI algorithm to actually generate handwritten digits that never have been written. We can use this GAN architecture in order to do so. So then we have a discriminator that we constantly pass real handwritten digits to. And then we classify them as real or fake. We will know which ones are real. Then we have the generated ones. Then we tell the discriminator that, okay, are you able to tell if this is real or fake? And if it's able to tell that it's fake, then we will retrain the generator until it becomes very capable of tricking the discriminator. This has enabled so many different use cases and applications. Only this kind of simple and intuitive model architecture. So another thing that we can do with style translation is that we can, for example, turn horses into zebras or the other way around. We can take a picture of a national park. Here you have Yosemite, and we can turn that picture into the style that it looks like in winter times without having taken the photo. You can take a photograph and have that in the style of like different painters. We can even dress up models for web shops and e-commerce. So if we have an image of a garment or some type of clothing piece, all of a sudden we can fit that onto models of different sizes, different shapes. Maybe you can even take a 3D rendering of yourself, and you can say, okay, how does small or medium fit me with this specific clothing article? That is all done by GANs. Amazon is definitely looking into this, and they want everyone to go into one of those crazy photo booths where they will map up your body dimensions. You will get a 3D avatar, and then clothing articles will be fit to you so that you know that you're ordering something that you won't have to return, because it's a big problem for them. They are losing. Yes. No, but only to not go through the hassle of like returning and be more confident and not have to go out shopping like on town.
Lots of female customers.
Male customers as well, but maybe even more females. Some people have used these types of algorithms also to earn a lot of money. Now in the boom of non-fungible tokens in the crypto space, etc., generative art has become a huge thing. But only 3-4 years back, it was not that common. But a couple of entrepreneurs in France, what they did was that they collected open image data from museums so that they could take thousands of paintings by masters of different styles. And then they trained one of these GAN models to produce paintings that never had existed before. So here is an example of a painting that was produced by that algorithm, and it was sold at Christie's for $432,000. This would only take 2-3 hours to do if you collected all of the data and trained the algorithm. However, Robbie Barat, so that was also a PhD student at Stanford who had created the code and open sourced it online. So he gave it away for free. He didn't receive any of the money. It was only the French entrepreneurs who went to Christie's, the auction house, to sell the painting. But this was the first AI created artwork to bring in a lot of money. There are lots more today, and we can talk about that more tomorrow. But so these GANs can not only produce artworks or different styles, etc. It can even generate content that looks very real. So on the slide here, you can see an image of a woman that never has existed. She has been generated by an AI algorithm. She has never been born. She has never walked the planet Earth. And what you can do is that you can go to the website, thispersondoesnotexist.com. And on this website, you have a GAN running in the background. Then every time when you update this website, you will see a picture of a new person that never has existed and that is being generated by an AI algorithm. And I would say it's very hard to distinguish this woman here from a real actual woman. And we can keep on updating it, so because they will have like young people, people of different genders, ethnicities, age groups, etc. This looks like a real child, right? And if we're interested, we can also generate things that are not humans. We can go to the website thisx.doesnotexist.com. And here you, for example, have a link to this cat does not exist. So here we have a cat that never has existed. Here we have another cat, and we can keep on updating. They also have this rental does not exist. So all of you have probably seen like Airbnb. These are generated images of an apartment, doesn't exist. The text for the ad has been generated by an AI algorithm, and the face for the host and the name of the host, everything has been generated by one of these gone models. Now, my favorite one, I told you earlier that I'm currently running 2 companies. So we have the website, this startup does not exist. What this does is that it generates a website for a company that no one has created, or an AI has created it. So here we have anymore, target a specific segment of the market is the tagline. Then we have a logo up there. We can also scroll down and we can see a couple of clients. So they will generate the images of the people using AI in productivity is what Filter is doing. You will have some features of it. You will even have like testimonials. You can sign up to a newsletter. So they have looked at a lot of different startup websites, seen a pattern, and then it keeps on generating. Here we also have like the CEO, this chief operating officer. We have some pricing for the service and what they do, if you want to join them. And if we update this, we will get a new idea for a startup. Some of them are actually quite good. So if you want ideas for businesses to start, you can go to this website. Now, have you heard about deepfakes before? I can see that a couple of you are nodding. And now, examples of that. So these are actual videos. Here I only have the GIFs of it, but we're going to look at the Tom Cruise one in just a minute. But the first deepfakes that were created that were really good was back in 2017, 2018. Then you could only do deepfakes of Obama, for example. So he has done many addresses to the nation in the United States. He will have been in this setting for hours. There is a lot of video data so that you can get the patterns from how Obama is moving, what his facial expressions are, how he's saying things, etc. So people could create deepfakes of Obama and other very, very famous people. However, that was 3 years back. And as I said, this technology is exponential. If I only had 3 images of one of you here from different angles, I could create a deepfake with you doing stuff that you never have done. That is very lifelike. Here you can see that people have taken the Mona Lisa and actually made her come alive. We only have one picture of Mona Lisa from one angle that was painted by Leonardo da Vinci 500 years ago. And it was earlier this year in like February when I saw the deepfake Tom Cruise videos that I realized, okay, now this is going to become a problem because it's impossible to distinguish this from a real video of Tom Cruise.
What's up, TikTok? You guys cool if I play some sports? I love it. More for the audio experience. As much as the momentum. Hey, listen up, sports and TikTok fans. If you like what you're seeing, just wait till what's coming next.
But so that was one example of kind of like state-of-the-art deepfakes. For many, many years, we have had the device seeing is believing. That is not going to be true anymore. In the very heart of the justice system, in courts, etc., a lot of the proof and evidence we bring forth would be photos, images, or videos of occurrences. It's very easy to fake that today. So you could have people doing things they've never done and then prosecute them for doing it. Or you can have politicians saying things that aren't true, that could sway elections, etc. So if we think that misinformation has been bad in elections up until now, I think this problem is only going to get worse. Now, another fascinating deepfake that I want to show you, and that's why I'm not doing the screen sharing yet, is, well, you're way too young to remember the moon landing, but you know that it happened. So we actually sent 3 people to space to land on the moon, 1969. Back then, Richard Nixon was president of the United States. And every president had people who write speeches for them. They don't have time to sit down and like come up with exactly what they're going to say. So the speech writers for Richard Nixon, they actually wrote 2 speeches. One was in the event that the moon landing was a success. That is the speech that he actually delivered. And the other speech was in event of moon disaster. So that is if Neil Armstrong, Buzz Aldrin, and the third person I can never remember crashed into the surface of the moon and didn't make it. Now, this speech was classified up until a couple of years ago. Then it came out of the archives, and a couple of computer vision researchers using these GAN models actually created a deepfake of Richard Nixon delivering the speech like the astronauts didn't make it. And this is what it looks like.
Good evening, my fellow Americans. Fate has ordained that the men who went to the moon to explore in peace will stay on the moon to rest in peace.
Now, I've seen the real address that Richard Nixon makes to the nation. And from those archives, I mean, the cameras weren't good. That looks more like a deep fake. So the deep fake is more real than the actual video, but you get the gist of it. It's very easy to do this today, and you can manipulate basically any content to get it to do and say whatever you want. Now, other application areas of deepfakes is that you can take a normal like 2D photo of, let's say, a landmark. Here we have a fountain. And if you only have a 2D photo of that, you can generate a 3D image of it today. This is research coming out of Google. So this is a normal photo from an iPhone that then gets turned into a scenery where you can see all of the details of the photo, and it becomes a 3D rendering automatically. Also powered by these GANs. And then the last thing I want to show you is this jukebox created by OpenAI. So OpenAI is probably the best AI research lab in the world. They are headquartered in San Francisco. And what they did was that they used these generative algorithms in order to be able to create music, which artists never had recorded. So there are a lot of examples here on OpenAI Jukebox, where we have like Elvis Presley singing in songs that he never has done, Katy Perry. If we go to fun songs, we can see we have a hip hop song here by Kanye West. I don't know, some of them are rubbish, some of them are really good, but let's try this by Kanye. I haven't seen that. I'll just sit up and open SoundCloud. And the beat is also generated. That's not by like a producer. Yeah, so it's basically Kanye delivering the 8 Mile, the Eminem. But so what this should tell you is that if you're pursuing a career as an actor, as an artist, as a painter, or anything like that, AI might be competing with you in a couple of years, or it's already doing that. But what I see as a major trend today is that actually many like visual artists, many people who are producing songs, etc., they can use this as a complement to augment their own capabilities. So I'm kind of tone deaf. I like singing, but it's only for my daughter that is like 1.5. but I can use an AI and then sing into my computer or at a microphone, and then actually turn that into beautiful singing. So I can hit the notes, etc. Maybe we can use those types of complements to enable us to do more. The last thing I want to show you when it comes to GANs is a company coming out of China. So this company was acquired by Tencent. I said that that was the Chinese equivalent of Google for many millions of dollars. What they're doing is product marketing in TV series and in movies for different like product placement for different types of companies, for different type of products. So here you can see a coffee company where they are creating billboards, advertising. They are relabeling storefronts, relabeling a coffee mug. Here's also like a billboard. And then they're even inserting the products into scenery. So I know a couple of people who work at Netflix. They are definitely experimenting with this technology. So I wouldn't be surprised if 1 or 2 years down the line, because advertising like this that can be so targeted is very valuable. That is the main revenue streams of Google and Facebook. So if you, for example, are looking for new sneakers in the morning and you're Googling like the Nike sneakers for running, and you spend 20 minutes doing that, I can almost promise you that when you watch Netflix in the evening, and if it's a contemporary kind of like TV series, your favorite characters that you relate to with the most are gonna wear those Nike shoes or similar ones. So that will push you to like be even more likely to buy them. And that would be a perfect way of Nike actually advertising to you as a consumer. So that was GANs. Now we're gonna switch topic again because I wanted to show you 4 application areas, right? Did you know that this worked? That AI was able to produce this? All of it?
Yeah, the bush stuff is
Yeah.
It wasn't on. It's creepy. I remember the Obama stuff coming out. It's freaking out.
But now it's so much more sophisticated. No, but I think it's very important for everyone to understand where we are, the state of this technology and what it can do now. Because it's going to transform like how we handle information, what is truth or not, what we can believe in, etc.
Is there any way that this could distinguish between
Mm-hmm.
have an algorithm that someone do something that they didn't? Could you do the reverse of that and have an algorithm that could detect whether the person is actually there or not?
Yes. So a lot of research groups today are working on deepfake detection systems. So basically what they're looking for are small pixel artifacts in the image that would say that it's generated and not from a camera. But it's almost like a cat and mouse kind of game. So just like we have ransomware and viruses being attacked on like modern computers today, deepfakes are going to get better. They will trick those detection algorithms. And then the detection algorithms will get better. They will catch the deepfakes. And I think we're going down that rabbit hole. But so again, to remind you what deep reinforcement learning is, because I think that's another frontier where we are pushing a lot of progress today. Then this wonderful slide again, very text heavy, very dense. But we have an agent in an environment that can take different decisions. We can simulate that. It can be a robot or it can be a player in a computer game. When we run those simulations many, many times, the agent will have selected many different actions in many different states, and it will learn an optimal policy. And that policy is like the probability of making certain decisions depending on what happens. This is something that has gotten very, very sophisticated in recent years. So here to the left, we have a video of a Go game. So Go is a board game. It's very like common to play it in Asia. It's been around for thousands of years. So it's almost like chess, but it's different to chess in one major component, and that is the number of actual outputs, the number of ways that this game can end. So the output space of this, now I'm going to get a little bit mathematic, bear with me, is 10 to the power of 360. That means a 1 and then 360 zeros after it. Do you know how many atoms we have in the universe? Yes. 10 to the power of 82. So that's a 1 with 82 zeros after. The number of ways that this game can end and the configurations how you can play it is 10 to the power of 360. So in 2015, so only 6 years back, when I spoke to some of the best AI researchers in the world at UC Berkeley, we had a discussion around Go as a game. And I said, okay, well, for AI algorithms to actually beat human players in chess, that's like evident. The output space is much, much smaller. But when do you think AI is going to beat human players in Go, the best ones in the world? And the researchers were like, yeah, that's 30, 40, 50 years out. 2 years after that, DeepMind, which is a daughter company of Google, located in London, they created AlphaGo. And they were able to beat the world champion in Go. Now that's crazy because you cannot simulate all the different games. So the AI cannot play itself and know exactly what it's going to do. It needs to work with limited information. But in simulations, this specific AI has only been trained on playing itself billions and billions of times. Now, we as humans have done this, as I said, for thousands of years. This is a great art in the parts of Asia where it's being played. There's a lot of honor to Go as a game. And here you can see the best player in the world, Lee Sedol, when he realizes that he has lost the first game. He was so confident that he would beat any computer. He was like almost laughing at it. There is a wonderful Netflix documentary on this. I think it's an hour or something. I would recommend that all of you watch it, because you can see when machines are starting to like take over human domains of intelligence and how that can be disruptive to the people who are actually acclaimed in those fields. But so that's the moment, and his face expression is like priceless. Anyway, deep reinforcement learning has been used also to play Texas Hold'em. So Facebook actually challenged the best poker players in the world, and they were able to beat them. Texas Hold'em is also a game with limited information. You don't know what the other player is doing, if they are bluffing or not, if they have the actual cards. But this became a pro player. You can make a lot of money by playing poker online and using this algorithm still, if you challenge people who don't know that that exists. And DeepMind also created an AI that was able to rank 99.8% best in the world out of all StarCraft players. So it's beating all of the pros, etc., in these games. Deep reinforcement learning can not only be used in game contexts, but we can also use it to train robots to do, for example, aerobics, like the one at the top here, and do flips, etc. We can take generic robot arms and train it in simulations to pick up different objects, and then it will be able to do that in the real world and almost generalize its intelligence. And here you have a video from a robotic hand trained by OpenAI, again, this research lab in San Francisco. It has only been trained in simulations to carry a Rubik's Cube. Bear in mind, this has to do with physics and gravity and the shape of the object, and also sort it and solve it. I would say that that would be very, very hard to do, like 5 years ago, almost science fiction. But today it works. We can also use deep reinforcement learning to train, for example, forklifts to work in manufacturing or storage places and pick up pallets all by themselves. We don't need forklifts to be trained by drivers driving them around, picking up camera data. But here they are trained 100% in simulations. Other things that deep reinforcement learning can do is that you can optimize the energy usage of data centers. So you can have one of these algorithms being deployed at a data center. Google did that for their own facilities, and they cut the cooling cost by 40%. That's a lot of money for Google to be saving, because the main thing you spend on when it comes to data centers is actually cooling down the equipment. A lot of hedge funds, a lot of crypto investors, etc., are using deep reinforcement learning to get an edge over their competitors and make the best investments. Sometimes that works, sometimes it can be disastrous. for your investment portfolio. An AI research team at Salesforce, also a San Francisco-like tech company. They have produced probably the most sophisticated ERP system in the world. They had an AI group that used this type of algorithm to be able to simulate a more fair tax system, because they wanted to find the optimal balance between productivity in a society and fairness. And they wanted to be able to inspire lawmakers and politicians to come up with new tax systems for new optimal gains for people. And we have autonomous drones, cars, etc. And it can even be used for drug discovery or medicines. We are in the cradle when it comes to this. It only started working 3 years back, 4 years back, many of these application areas, and a lot is going to be transformed when this gets even more capable. So we're going to switch gears for the last time now, and this is the fourth area that we're going to cover. And this might be the most exciting area right now, because this is where we're seeing the most progress. So only for a computer to be able to understand language, know our intent, and so that we can communicate with the computer, or that it can analyze all of the text that is online. That has been very, very noisy up until 2018. And now we're starting to see capabilities that even exceed human capabilities in this field. Examples of natural language processing, or NLP, can be that we take speech and translate that to text. So that is me speaking, and then we can get that into text into a computer, and it can also be text to speech, so the other way around. We can have machine translation. We can translate from English to Swahili and back. Summarization of text. So let's say that you have a novel in the computer and you want to get a summary of that novel. You can have an AI produce that for you. Sentiment analysis is finding out, is this, for example, a positive or a negative product review? Amazon is using that a lot when people give feedback on what they have bought. Maybe they don't want to have people reading all of that. We can have text generation. So that's basically an AI that completes text or writes something from scratch. And also question answering. And that would be sort of like Google. We would ask a question and get an answer out from the AI. Again, only, I would say, 10 or 15 years back that we could speak to our devices and they would understand us would be science fiction. Today, we take that for granted. I speak to my Alexa almost on a daily basis, asking it to play radio or something like that. Now you can even have conversations with these voice assistants. So you can ask them things about physics, and you can ask follow-up questions, and they will find the information on Wikipedia. And the progress here is very, very fast. As I said in the beginning, I worked with the Amazon Alexa team quite a lot. And only the capabilities that they are demonstrating that they haven't released yet are very cool in the dynamics you can have in the conversations with a voice assistant. And I don't know how many of you read the paper, The Economist, but what The Economist did in the beginning of 2020 was that they interviewed the pre-trained language model GPT-2. So GPT-2 is a large language model. It's actually huge. And it had been trained to do text generation, question answering. It can do summarization, sentiment analysis, translation. It can do everything. So The Economist, they decided to put this AI to the test because OpenAI said that it was capable of carrying out any task. So they actually had a journalist interview it for 3 pages straight. And if you've read The Economist, you know that the text is very dense. So this is only the beginning of the article. You have the journalist here asking, "Greetings, GPT-2. Have you done an interview before?" And the AI answers, "I'm not going to lie, I did not come prepared," and it adds a laughter to it. Now this interview stretches on, as I said, for 3 pages. And I can promise you that this AI is more eloquent than most humans. It's definitely more sophisticated than what I would be in a situation like that if I had to answer questions from an economist journalist. Now, this was back in the beginning of 2020, and GPT-2 is from 2019. A lot of things has happened since, but I can only show you because there are open APIs where you can test this. I did it for the context of this program. So the input for text generation here is what you can see at the top. So I only wrote, today Alexander Fred Ojala is hosting an AI and blockchain masterclass in Oxford. The presentation demystifies. And then I didn't put in anything else because I wanted the AI to complete this. This is also the first output that I got. You can get hundreds and choose the one that is best. But then the AI says, and this could have been a real article, demystifies the technology as a means for transforming business models, government services, and the economy for all. And then it adds a quote. The fear of this change is palpable. People clinch to the old ways that don't meet the requirements of the future. Professor Ojala, so it ranks me as a professor, thank you, is a qualified mathematician, technologist, and board member of the Global Blockchain Council. So you can see it's a little bit noisy, but at least this could have been true. It's like a human has written that. It's not, if I didn't know the context, I wouldn't be able to decipher if it was noise or not. But GPT-2 was 2.5 years back, or 3 years back. You can see GPT-2 down here. So that had 1.5 billion model parameters. And you can see the trajectory that we're on. So in the beginning of 2020, what we saw with the Economist interview, then state of the art was 17 billion model parameters. Last summer, OpenAI released the next version of GPT, and that was truly astonishing. Like it can do things that was unimaginable before. So this has a total of 175 billion model parameters. That's the number of parameters you can change in order for it to make decisions and do different things. It has been trained on 300 billion tokens. That's the number of different words it has been trained on. And only training this AI one time has an estimated computing cost of $4.6 million. That's training it one time. I can promise you they have trained it many, many times to optimize it at OpenAI. And the most limiting factor here is not the number of model parameters, but it's the amount of data that OpenAI could find to train this. So they used all relevant text data they could find on the internet. This is all of Reddit that was relevant, all of Twitter that is relevant, all of Wikipedia, many news sites that are open that they could use. But still, what is limiting this is that we don't have enough text on the internet to make it more capable. However, there was breaking news only 6 days ago. So I had to update my slides because now Microsoft and Nvidia has created a 530 billion parameter language model. Unfortunately, it's not open to the public. But now we're talking about billions of weights parameters, ways of creating these rules. This is only 2 orders of magnitude less than the connections we have in the human brain. And that's for one AI model. And you could see the trajectory that we were on. It's exponential. These are going to get bigger and bigger. Now we only need more text data on the internet, but maybe they can generate them for themselves. So a couple of examples of what you can do with this technology now. We can go to the company copy.ai. That's their URL. What they let you do is that you can create your own copy for online marketing. You can create copy for your own brand. If you want to advertise on LinkedIn or Facebook, you can create that type of content. If you want to create a website for your company, they let you do that. And they will generate many different examples if you only input the name of the company and 6-7 words of a description of what you're doing. Then you can save the best ones. And all of a sudden, the AI will be nudged to producing output that is similar to that. And you don't need a copywriter anymore. If we scroll down here, you can see that they do digital ad copy, social media content, website copy, e-commerce. They can even write blog posts for you and do sales copy. Now, Copy.ai and their models have only used API access to GPT-3 from OpenAI. API access basically means that they are using whatever OpenAI has trained. They nudged it a little bit to their own domain, and they have raised $20 million for this now. In order to do that yourself, if you had the access to GPT-3, which you can get for free if you're a student, would take 2-3 days of showing examples of digital copy. $20 million because they have packaged it in a good way. We can also do, for example, here is a video of a functioning web application, if we can load it. So this is, again, GPT-3 that has been trained to take in English language, add a button that says add $3 and a button that says withdraw $5, then show me my balance. That's the description for a web application. It takes a little bit of time of loading. Then you can see the web app being rendered here. But what is truly remarkable is that you actually have the source code. So you don't need a developer to write the code or program for you anymore, but the AI programs for you. And this is 100% compiled. It works really well. So now the person inputs it again and changes this, and a button that says, give away all my money. Regenerates it. And then the new component will be shown once that is loaded. There we go. And the functionality of that works. So we might not need programmers soon. We might only need these large-scale models because they can be trained on source code that is published in these GitHub repositories, open source, online. There are hundreds of examples of fascinating things that people have done with these models. So you can also create a search engine that works almost as well as Google. They can find information for you. You can generate UI designs, so even design components, not only like source code. For it, you can write as a lawyer. That's something that I told Katja earlier. You can autocomplete your emails. People in high school have even produced essays. So if you need to write a paper about Shakespeare, you can start that paper, write 2 sentences, and then it will autocomplete it for you. And a lot of students have received a grade of A+, turning that in. And a lot of people have even created blog websites. So there is a lot of blogs handle the topic of like productivity. When should you wake up in the morning? Well, you should get up at 4:30 a.m. You should drink some water with a squeeze of lemon. Then you should take a cold shower. You should meditate. You should run, etc., etc. And then you will be very productive, right? One person took all of these productivity blogs, threw it into GPT-3, started generating new articles, and ranked as the top productivity blog in the world. That was not a human that distilled the information, but an AI. So in the beginning, or like mid part in part 1 earlier today, I said that we only have narrow AI today. AI that works really well in well-defined limited contexts, and that we could see some seeds of general artificial intelligence. This is what I would call general AI in some sense. Because in order to power these use cases, so for example, to make GPT-3 translate between Swedish, my native language, and English, I only need to show it one example of a Swedish sentence and an English sentence. Then it will be one of the best language models in the world to do translation. In order to have that self-coding application, show it 3 examples of English language, and then what the output is in code. And then it will look among all of its billion parameters, whatever is descriptions of code that has been done online, and it will do that kind of mapping. So you don't need big data sets anymore. You only need a handful of examples in order to power new use cases. Another lawyer example here. So whenever you set up a company, for example, then there will be a lot of legal clauses that you don't understand. There will be so many documents, and many times I only like sign it because I don't want to spend time with a lawyer going through everything. Now, GPT-3 has been trained to take legal clauses and translate them into plain English. So if I were to read this paragraph up here, I would barely be able to understand it. However, if I looked at this translation here, so it says, if the startup or company is wound up, then they close it or shut it down, then the Series A investors will be paid back at least what they invested, and they will also share any leftover assets with ordinary shareholders. I can understand that. Very, very happy to see those application areas. Last but not least, we can also have AI summarizing AI. So a little bit of meta perspective here. But as a researcher in this space, it's very hard to keep up with the frontier constantly. I don't have time anymore to read all of the research papers that I want to read, because there are way too many talented people publishing now. That was not the case 5 years back, then it was still possible. But so a research group, they created Semantic Scholar. What that does is that it looks at research papers and then produces a too long didn't read section that is very, very short. So let's say that we wanted to look at graph neural networks. Let me zoom in here. So let's say that I wanted to get to know graph neural networks. I haven't read any research papers on it. Then I could only go through here and we would see this work characterizes discriminative power of popular GNN variants, and it would actually say what's in the paper and what the takeaways are in like 1 or 2 sentences. It's so comfortable. And this is actually a tool that I use in order to scan research. Yes.
How accurate is it? Like I can just put like a whole 1,000-word essay into like 2 lines. Is that how accurate is it? The 2 lines?
Sometimes it produces a little bit of gibberish and you don't get the true like core essence of the text that you feed in. But most of the time it's accurately good, or it's, yeah, way too good.
Books and everything.
Yes.
Okay.
No, you can train it to handle any type of text. But so as a summary for natural language processing, because that's also one of my core like research areas, soon we won't have to answer text messages, email. When it comes to writing movie scripts, for example, you have a lot of people writing like drafts for books or movie scripts. In order to complete them, you can have an AI that assists you, that produces like drafts, that changes some paragraphs, maybe makes them better. So it will be a tool that can be used in order to perfect your work. I don't think it's going to replace humans. It's not that sophisticated. It can handle contexts perfectly, but it can definitely aid us. So what I see is that we can have an AI that, for example, writes a script for a TV series, and then we can have a generative algorithm that actually produces that for us. So we will have the complete TV series being done by 2 AI algorithms. In order to wrap up, if you don't have any questions around this, we have done all of the application areas, the use cases now. And I hope that this was like eye-opening to you, because we have gotten so far in only like 2-3 years that it's a little bit crazy, to be honest. I would never have predicted that 3 years back. And then I was still like in the midst of this field. But now I want to turn to an industry perspective around this. So if you were to like make a career within AI, what is important to know? And how is value created with this technology? And the first thing that I want you to know is that most companies today, except for Google, Amazon, Facebook, all of these like tech giants, they are at the beginning of their AI journey. They basically don't know that these tools exist. I do presentations for many executives and boards of big companies or startups, companies in many different fields and domains. They don't know how they can leverage this technology to create value because it's so new. However, just like the internet or a computer is an important tool in order to do work today for every company, that is also my thesis when it comes to AI. It's relevant for every industry, and only what we can do today with AI can actually automate processes, help you make better decisions, analyze things in a much better way than we humans can do. So the faster the companies can transition to actually leverage these technologies to create value and be competitive, the better that's going to be for those companies. And we also saw that on the top 10 list of the most valuable companies in the world. All of them are data-driven today. And now, if we think about the AI journey as a step-by-step process, it can look like this, that you have most companies here to the far left, they are passives. They might be observing that something is happening, but they haven't started using the technology yet. Some might develop like proof of concepts or demos of certain application areas or use cases. They will be experimenting a little bit, but it doesn't change their like core operations and how they work. You will have some companies that are using that in order to operate. So we have Maersk, that's a global like supply chain shipping logistics company. They are using AI in order to optimize supply chains, transport routes, etc. You might have some companies that are best practice for certain verticals. Tesla is a good example. Self-driving capabilities, some computer vision, and also their manufacturing practices are probably the best in the world. Definitely AI-driven. And then you have a couple of companies in the world who are pushing all the boundaries. And Google, Amazon, Facebook are some examples. Now, the main reason why Google and these very innovative companies concentrate on AI so much is because their most valuable metric for success is rate of experimentation. They care about how much money they make, but in order to make more money and in order to keep their market share, they need to constantly be innovating. So they are doing experiments that they are tracking with AI and self-optimization. So they would, for example, have 10,000 different versions of their ads engine running at the same time. And they will see who is performing best in order to convert customers. And then they will switch over to that tree and keep on optimizing. If you are a company here or an individual here that you haven't used this technology yet, what you can do is that you can piggyback on the success and capabilities of the companies here, because they are actually competing with one another. So Google has a cloud initiative. Amazon has Amazon Web Services for cloud services. And all of them are giving you AI services that you can buy. And because they're competing, the prices are very low. So if you want to do computer vision, you can leverage the capabilities of Google. You don't have to get your own data set and train your own classifier, but you can get the best one in the world and be data-driven right away. So you don't need to do step-by-step if you don't want to. You can also look at what the best models in the world can do. Now, many times when people embark on an AI journey, then it will fail. This has been the case for the past like 5-7 years. A lot of companies have explored this. A lot of individuals are trying to do pushes, but they won't end up delivering value. The main reasons for that is that, for example, many companies will have legacy IT infrastructure, old databases, spreadsheets that are siloed at different computers with different people. They cannot aggregate the data, etc. The algorithms will perform really badly or poorly. They will lack in-house talent. They don't have any data scientists or machine learning practitioner, etc., etc. But there are many reasons for it. And a fascinating fact is that 60% of all initiatives within companies today actually fail, even though the technology is very robust and it actually works. So then I'm going to conclude with a couple of pointers on how you actually create successful AI projects. This is something that I hinted to in the last presentation as well. But whenever you build a system, the actual code that is the algorithm, that is the model, is a very tiny part of the full system. You need to be a good software engineer so that you can handle different types of inputs data. Then you can store that in, for example, spreadsheets or tabular data. You can store it in a database for long-term storage. You might even store it on a blockchain. And then you get some output. You need to handle that as well. That is traditional software engineering. And then you have a feedback loop. The actual machine learning is a very, very small part of this. And it's not only like the data system that we have prototyped at Berkeley. Google is saying the same thing in a research paper. This is a research paper that is called The Hidden Technical Depth of Machine Learning Systems. And they say that the AI code is this small box here, and everything else is actually powering the system. So it's not that only AI or the algorithms, the models, they are not the magic, but it's everything that you build around it and how it fits into a context. Again, I would like to emphasize, whenever you're doing machine translation, text recognition, video labeling, chatbots, speech to text, etc., don't do that yourself. Don't train your own model, don't collect your own data, but do it through APIs from the best companies in the world, because they have an army of engineers that are perfecting this all the time. Another thing that I want to say is that, and this is something that we're going to experience tomorrow, but whenever you're actually building a system like this, what takes time is to clean up the data and to get the data into the right format so that you then can throw it into an algorithm. It can train itself, get the rules in order to be able to make predictions or inference. 90% of the work is on only like managing the data, creating feature transformations, etc., and not around the mathematical statistics part. Many people think that in the beginning. And last but not least, big data was a buzzword, I would say 2012 to 2018. Now I spoke about GPT-3 and the big language models. You only needed 1, 2, or 3 examples in order for that to be really good. You don't need gigabytes or terabytes of data in order for a system to work. Many times it's enough with like 1,000 records, and then they can be very powerful. So the threshold for doing something that is valuable in the world today is very low. And only look at copy.ai, that example that I showed you. They could have had 10 examples of copywriting that they generated from input. And all of a sudden they started a company, they only produced a website for it, and they were able to raise $20 million. That effort is very low in contrast to the reward that they could get by only understanding that this is an opportunity. So resources for tomorrow, if you want to look at the website, please do so. It was alex.fo, not bit.ly. And then I can stick around. I can take any questions, or you're also welcome to go and enjoy your evenings. Yes. But now you can call yourself AI experts if you can remember everything that I said now during these 2 sessions.